Hello everyone, this is Diti Chaudhary from the School of Computing Science and Engineering, Calcutta University, and the course code of the subject is BSCS2380. The course name is Cybersecurity. So in today's class, we will read about primarily testing. Now let's see what is primarily testing. So primarily test is an algorithm that is used to determine whether or not a given number is prime. Prime numbers play significant role in different cryptographic algorithms. That's why for any large number, whether that is a primary number or not, is very necessary to test. So for primary early testing, there are two methodologies that are being used. One is the deterministic one, another is the probabilistic one. In case of deterministic primarily testing algorithm, a number is being taken and all the test parameters are passed to the number. If the number satisfied all the test parameters, then we can say it is deterministic. It will be definitely a primary number. But as this is not extensively used because of the slow processing of this algorithm, and AKS testing is the example for deterministic primary testing. Now for probabilistic primary testing, what we do, we have some kind of arithmetic conditions which are needed to be satisfied for some set of numbers. If the numbers are having higher probability to pass or satisfy those parameters, then we can say the numbers are prime. So these are not that much definite as the deterministic one. Now, before going to test for any number, whether the number is primary or not, what we can say, we are having certain properties, we will have to go through those properties. The first property is the congruent modular A. So this says if a number like A mod n is equals to B mod n, then we can rewrite it as A is congruent of B mod n whole square. So we can apply this in different ways, as you can see here. Okay, if we are having this, these are the equivalent relations, congruent relation. So if we are having 23 congruent of 8 mod 5, so like if we are having a you can see that if we'll subtract 23 by 8, then we will having 15, and 15 is some multiple of 5. 15 is some multiple of 5. Similarly for minus 11 also you can see. So what we will do, from 11 we can subtract 5. We will have 6 minus 16, and which is equals to 8 star minus 2. So some multiple of minus 2. So like some multiple of minus 8. Sorry. So we can likewise we can do for this also. So here are some properties of congruency. So what are the properties? If we are having the congruence A, congruence B mod n, then we can say that this n is n is equals to A minus B. Also some modulo like m star A minus B, we can say this. So then if, as we have seen here in this example, this works fine. So now if A congruence of B mod n, this implies that B will be also congruent of A mod n. This is the symmetrical property. And there is one transitive property that is also holding here. Okay, if A is congruent of B mod n and B is congruent of C mod n, then we can say A is congruent of C mod n. Now here we can see, okay, if any integer p is greater than 1 is a prime number, then p have only two divisors. One is plus minus 1 and another one is plus minus p. That is, suppose we are considering 13. 13 is a prime number. So if 13 is a prime number, it is having two divisor, plus minus 1 and plus minus 13. You cannot have any other divisor. 13 will be divisible by plus minus 1, or 13 will be divisible by 13 itself. Now, if we are having any number that is greater than 1, we can write the number as the product of multiple prime numbers. How we can write it? We can take any example. Suppose we are having any number, any random number you can choose. Suppose this is 60. So what we can do? We can write 60 as the multiple of 2. Then again multiple of 2, then again multiple of 3, 2 2s are 4, then this is 5. Right, we can write in this way. So see, all these are prime number. These are only divisible by the number itself and 1. Now here are some other example of prime numbers which can be divisible by the prime numbers itself. So for that, the condition will be that P1 is less than P2. For this, the condition will be P1 less than P2 less than Pt. So you can see here that 2 is less than 3 is less than 5. Now this can be written as A is equals to pi of P belongs to capital P, small p to the power A, and then small p. So what does this mean? This is the cross product, that this one, the multiplication one. And we can, if we'll write in this format, how can we write this? So suppose there is 12 or 18, whatever number you want, or 91, whatever number you want to write. Let's suppose it's 91. So what we can see, if we'll divide 91 with 7, the result will be 13. So I have 7 1 and I have 113. So I will write here, this is A13 and this is A7. So if we can write 91 is the cross product of A7 and cross product of A13. A7 is having value 1, that means we need only 1 7 and we need only 113 for A13 is equals to 1. You can see here, you can see for 12 I am also showing it. For 12, if you divide 12 with 2, it will give you 6. Then if you give it 2 again, it will be 6. Now if you write it in this format, where how can you write it? There is 2 and 3. So A2 is present and A3 is present. Now the number of A2 that are present is 2. Number of A3 is 1. As you can see here, we can write 12 in the form of 2 cross 2 cross 3. So there are two numbers of 2 and 1 3. Right? So now here are two properties of prime numbers. As we can see, the first property says that if we are having A as this p to the cross product of p to the power A p, and p is having a value of cross product of p to the power p, then we can write a k which is equals to p to the power kp, such as kp is equals to ap plus bp. Here is one example. As we can see here, k, suppose we are having k, so we are writing it as 12 cross 18, and this can be written as 2 to the power 2 cross 3 and cross 2 to the power 3 cross 2. So we can write the say 12 as this, and we can write 18 as this. Now this is equals to 216. So what we can write, if we are having k2, then we can write 2 plus 1, this is 2 and this is 1, so we can write it as 2 plus 1. And as we are having k3, so we can write it as this is 2 and this is 1, so this will be 3. Now if we'll write in the similar way, 2 to the power 3 cross, we can write 216 as 2 to the power 3 cross 3 to the power 3. So we can put the values directly and it will be 8 cross 27. So we can write mm, the same number, we can represent it different way. Now there is another properties also for divisibility. If we are having A and B in the similar way as it was in the previous condition, then if we do A divided by B, then it will be AP AP less than equals to BP. So how we can prove that? Suppose A is equals to 12 and B is equals to 36. 12 can be represented as 2 to the power 2 cross 3 to the power 1, and 36 can be represented as 2 square cross 3 square. So here the value of A2 is equals to 2, which is, you can see the value, same value as B2. If we will write 12 as 2 square 3 to the power 1, so this A2 will be 2 because of this, and A3 is equals to 1. Now if we'll write 36 in terms of 2 square and 3 square, then here B2 is equals to 2 and B3 is equals to 2. So what we can see, that if we'll write in this format also, we will find that A3 is less than B3, although A2 is equals to B2. So in this way what we can write, that's how we can see AP less than BP. We can take any other example and we will see the same thing. So primary testing is done using Miller-Rabin test. So this is a kind of testing where used for which is used for large number of primary liti. And here we can say that firstly, any positive odd integer n greater or equals to 3 can be expressed in the way n minus 1 is equals to 2q. KQ, and where K is greater than 0 and Q is odd. So here is one example. As we can see, if suppose we are having any odd integer, we can write in this format. So I'll give you one example of that. Suppose we are having any number, you can take, suppose it's 25, this is odd, and if we can write it n minus 1 is, if n is equals to 25, we can write n minus 1 is equals to 24. So can we write 24 in terms of this? So see, 24 can be written as 2 into 12, and also we can write 12 as 2 into 4 cross 3. So that means we can take k as this is definitely greater than 0, and we can have a q is equals to 3. That means this condition is satisfied. To see this, note that n minus 1 is an even integer. See, this is n minus 1, which is even. Then divide n minus 1 by 2 until the result is a odd number, that is q. So if this is q, I already have said if this is q. So t is the k is the total number of divisions. So you can see, if we'll divide 24 by 2, this will be 12, then this will be 6, then this will be 3. So now if we'll write here, so this can be written as 2 into 2 into 2 into 3. That can be written as 2q cross 3. So that this one is q, this one is, we can say this as q, k, and this is 2. So we can express any number likewise. If n is expressed as a binary number, then the result achieved by shifting the number to its right end until the rightmost digit is a 1. So if we are doing the same thing for binary number, you can apply this last property to find out whether the number is prime or not. So here this is the algorithm that is being used, and we can write the algorithm in the similar way as we have given here. If n minus 1 is equals to 2kq, we will have to find out k and q in a manner, and if a to the power p mod n is equals to 1, then the number is inclusive, otherwise the number will not be. If for j equals to 0 to k equals to 1, k, k equals to 1, do if this one is satisfied, k minus 1, sorry, this will be minus 1. So if k minus 1, then a to the power 2 jp mod n must be equals to n minus 1. So this is j or k, whatever, as we have written here, and k, that's why we have taken here j. So then we can return this inclusive, otherwise it will be returned as composite. So likewise we can test, and there are two properties of the prime number that are being used. The first property says if p is a primary and a is a positive integer less than p, then a square mod p is equals to 1 if and only if a mod p is equals to 1, or a mod p is equals to minus 1 mod p is equals to p minus 1. You can take any example of this to verify whether this is possible or not. So if you can write here, if a mod p is equals to 1. So suppose 13 mod 2 is equals to 1. Suppose that's true. So now if I'll do 13 square, that is 169, then we will do mod 2, then definitely this will be 1. Why? Because there is 2 will be divisible by 168. So 169 minus 168 is equals to 1, and if we'll divide 168 by 2, the result will be 84. So the quotient will be 84 and remainder will be 1. So that's why this is satisfied. Another one is, by the rule of modular arithmetic, a mod p star a mod p is equals to a square mod p. So we can apply also the same thing, and thus if either a mod p is equals to 1 or a mod p is equals to 1, a square mod p is equals to 1. So we can prove the previous property by this property also. Right, so this will be 1. Again, if I'll do mod a mod p, this will be 1. So now if we are having 1 and we are multiplying these two numbers, then the result will be 1, which is said here in this property. Conversely, if a square mod p is equals to 1, then a mod p whole square is equals to 1, which is only true for a mod p is equals to 1. So something, if we are having any remainder which is 1, then the result will be also 1. The second property says what? The second property is saying that p be a prime number greater than 2. We can write p minus 1 is equals to 2 to the power k q. We have seen these properties earlier. AQ is congruent to 1 modulo P, that is AQ mod P is equals to 1, or equivalently A to the power K is congruent to 1 mod P. So any number, if we consider any number, then these are the properties which will be considered for prime numbers. This is the first property. The second property is what? For any number a to the power q, a to the power 2q, a to the power k minus 1 is congruent to 1 modulo p. Then there is some k which is having the range of 1 to k. There will be some j such that 2j minus 1 uh, q mod p is equals to 1 mod. So whatever we will write, suppose in this way, if we will write a mod p, we can repeat this the same thing n times and the result will be 1, because for 1 it is 1, so for whole to the power n it will be 1 to the whole to the power n. The result will be 1, thus this is satisfied. So